last week, before our quiz and everything, we were doing sections 3.4 and 3.5, okay, particular triple integrals in XYZ. And for any solid region S, okay, the triple integral of any given function f of x, y, z on that solid region, okay, it's done in an iterative process, done inside out. And if this function represents the density, then this is the mass of the solid. And a more specific case is if f of x, y, z is 1, then the triple integral of 1 dv over s would give you the volume of s. Okay, so that's where we stopped, and we did a bunch of examples in a variety of situations, some of them which we did not compute because those were regions where some other coordinates would have been more appropriate. Okay, so that's where we stopped. So any questions before we move on to the next part? No? All right, so the next two sections, again, some of these are covered together because they kind of deal with the same material in two sections, so it makes sense to combine them. Okay, section 3.6 and 3.8. And I think we did a few examples last week to kind of motivate these kinds of coordinate systems, okay, cylindrical and spherical coordinates. So today we will introduce both the coordinates and also do a few examples in the worksheet. And if we don't get time to finish everything, we'll finish it off tomorrow. Okay. All right. So just to remind you what we saw in R2 in section 3.3, we saw polar coordinates. Okay. So that was on the XY plane. If we have some kind of a circular region in R2, then all of you know that if this is your radial distance at an angle theta, okay, then x equal to r cosine theta, y equal to r sine theta, and x square plus y square is r square, and dx dy or dy dx would be, or dA would be r dr d theta. Okay, so in this case, your r is any positive number depending on the radius of the circular region. Okay, theta has some finite limits. Theta goes from 0 to 2 pi in one rotation counterclockwise from the positive x-axis. Okay. The good thing is that cylindrical coordinates is just a 3D extension of polar coordinates. Okay. So there is nothing entirely new happening here. So cylindrical coordinates extend polar coordinates to R3. Okay. When I say extend polar coordinates to R3, that means you already have something on the XY plane. Okay. We just give it a Z extension. So the Z direction gives the height, okay, as usual. Defines height. Okay. So, but we have to draw three axes now, and let's see how well we can do this. This is your x, y, which is the level ground, and z, which could go below or above the xy plane. It depends on your solid. And then you have your regular polar coordinates. Remember that your angle theta is measured from the positive x-axis. So if you have a radial line here, then this is your theta. Okay. Everything should make sense. This was your x-axis there, and now theta is measured on the XY plane from the x-axis. So that is your point P. And then it gives some kind of height element here. So now we have a point, say P1 in space, okay, XYZ space, and it has coordinates of R, theta, and Z. Okay, so PXY is on the XY plane. And then you give it a height along the Z axis. It could be above or below it. Okay, it doesn't matter because Z just goes from negative infinity to positive infinity. So that's one of those directions in which there is absolutely no limit in terms of where it could go from or where it could go to. Okay, but the third coordinate is just an extension of polar coordinates with a height element to it. So cylindrical coordinates is defined in terms of R, theta, and Z. Okay? And that's why it's such an easy extension of polar coordinates. All you're giving is an extra letter there for the height, right? And then your x is still r cosine theta, y is still r sine theta, and z is z. Okay. So dv, the volume element, would be then dA times dz, because that's going to be area times height. And that's going to be r dr d theta times dz. Okay. Of course, you could change that order of r dr d theta dz depending on your convenience. Okay. So this could be in any order you wish. Okay. So theta, r goes from 0 to infinity. Okay. Radius should be positive. Theta goes from 0 to 2 pi, no change, okay, because it's still going on the xy plane like this. Okay. Z, in theory, goes from negative infinity to infinity. Okay. Though all the solids that we will be doing will have finite height, but there is no restriction because the cylinder could extend part above or part below the xy plane. So the z axis or the z variable is capable of doing any kind of height, whether it doesn't have to be strictly positive. Okay, radius though has to be positive. So that is cylindrical coordinates. So any questions before we start doing examples? Well, let's first check whether this is actually true. Okay, so before we start doing more fancy things in the worksheet, find the volume of a cylinder of radius capital R and height capital H. Okay, and I hope all of you know what to expect out of this. A cylinder, this is what it looks like. Okay. It's a circular cylinder, just to be more precise. Okay, so the base area is pi r square. Okay, the height is h. So maybe from your previous math classes, or maybe from high school or middle school, you know that the volume of a cylinder, circular cylinder, okay, would be just pi r square h. So let's see if that makes sense with our cylindrical coordinates. Okay, so here we have a little r going from 0 to capital R, okay, because the radius is r. Height goes from 0 to h. Okay, so you could define the z any way you want, such that the overall height is h. Okay, it doesn't have to be 0 to h, or you could do this as well: negative h over 2 less than or equal to z less than or equal to h over 2. Okay, anything as long as the net height is h. Okay, but I think this is easier. And it's a full circular cylinder, so theta goes from 0 to 2 pi. So the volume of any solid would be the triple integral of 1 dV. Okay, and this is your solid S. Okay, and that's going to be equal to the triple integral of 1. If you want to do z first, that's okay. So dz and then r dr d theta maybe. Okay. And all these are constant limits, so it doesn't really matter which one you do first. So it's 0 to h, 0 to capital R, and 0 to 2 pi. Okay. And I think it's pretty obvious as to what's going to happen here. You can separate it out: 0 to 2 pi d theta, 0 to r dr, and 0 to h dz. Okay. So that's going to be 2 pi times r square over 2 times h. Okay, and that's pi r square h. Oops, pi capital R square. So there is nothing groundbreaking in the volume of a cylinder if you use cylindrical coordinates, and you know the limits for r and the height. Okay, that's what we have. Any questions on that? So that kind of verifies that our cylindrical coordinates make sense with what you have learned so far. Okay, and it also makes sense with your intuition of any solid in general, that it's a base area times height. Okay, so everything checks out. Any questions before we start doing the problems in the worksheet? All right, I think I forgot to upload my worksheet here, so I need to give me 1 second. Okay. I knew there was something that I was forgetting. And okay, so let's see if it is ready to be uploaded. Yep. All right, so this covers sections 3.6 and 3.8. Okay, you can see it's a pretty long worksheet because I've tried to include as many problems as possible, but we'll go over it one by one. Okay. So the first one, it's to find the volume of a solid, which is, well, it's kind of a tricky wording there. It says below by the half cone given by this equation and above by. Okay, so it's not below and above, it's the other way, right? Below by means it's above, and above by means it's below. Okay, and sometimes students get confused as to what this means. The half cone, remember that your cone in general has two pieces. Okay, this is what a general cone is represented by: z square equal to x square plus y square. So z is plus or minus square root of x square plus y square. Okay, which means it is the double cone that goes like this. So when the question says the half cone, okay, which is right here, that just means the upper half cone. Okay, which is this part. Okay, so it's not slicing the cone in some weird way. It's just the fact that the bottom half of the cone is not relevant for us. It's just upper half cone. Okay, So hopefully that's not going to confuse you. Okay. So now the shape of this solid S that we have given here, it's going to be below the, remember that z equal to 6 minus x square minus y square, it's a paraboloid. Facing down, okay. And z equal to square root of x square plus y square is the cone that we have there, okay. So it makes sense that you can form a solid which is bounded above by the paraboloid and bounded below by the cone, okay. So this is what this entire solid region looks like. So this is the top part of the solid, which is given by z equal to 6 minus x square minus y square. And this is the bottom part, which is z equal to square root of x square plus y square. And there are already hints in the problem that tells you that using polar coordinates might be useful, or cylindrical coordinates might be useful. We have a minus x square minus y square, okay, which means that 6 minus r square. And this is the square root of r square, which is r, okay. So I think if those two things are not strong enough hints, then I don't know what could be, because it's really telling you that, you know, cylindrical coordinates is the way to go here, okay. So use cylindrical coordinates. Of course, I always need more pages, so let's page it. Okay. So the z limits are pretty easy, right? It's going from the cone below to the paraboloid above, so it's going to be r less than or equal to z less than or equal to 6 minus r square. Okay, usually the z limits are pretty easy because they tell you the floor of the solid and also the roof of the solid. Now, can any of you tell me what the limits for r will be? That's the only challenging part of this question.
0 to 2.
0 to 2. Maybe that is correct, but I don't see how it's 2. I think you're right, but you know, with the 2 is not really obvious from the questions. How did you get 2?
You find the radius where the paraboloid and the half cone intersect.
So that is a circular disk here, right? So the intersection, that's right. So let's do that. That's always the way to go. Whenever two solids intersect, you try to find what exactly would be the projection of the intersection on the xy plane. Okay. So intersection would be when those two are equal. And since we're already working in terms of r here, let's just use that. Okay, 6 minus r square equal to r. Okay, it's a quadratic, so you have to kind of rearrange the terms and put it properly. So it's r square plus r minus 6 equal to 0. Okay, and you could factor it, or you could use a quadratic formula here. So it's going to be r plus 3 times r minus 2 equal to 0. Okay, and this is where you have to be careful. So looks like we have two values for r, okay, r equal to -3 and r equal to 2. But I think you decided to go with r equal to 2. Why?
It's positive.
Yep. R cannot be negative, so it has to be r equal to 2. Okay. So this is not one of those cases where you consider all possible values. Okay, the radius has to be strictly positive. So the limits for r in this case would be from 0 to 2. Okay. Nothing fancy about theta. It's always the full circular angle. So 0 less than or equal to theta less than 2 pi. Not always, unless the problem says it's sliced somewhere. Okay. In this case, it's not. So that's it. Okay. So we have the z limits here and the r and theta limits. Okay. You should keep in mind that z depends on r. Okay. So don't don't start splitting the integral from the very first step. Be careful when you're doing this. Okay, so the volume would be the triple integral of 1 dv. Okay, and that's, so let's set it up first. So z has to be done first because z depends on r. Okay, so the z goes from r to 6 minus r square. Again, it's not the square root of r, it's square root of r square, which is r. Okay, r goes from 0 to 2, theta goes from 0 to 2 pi 1 dz r dr dθ. Any questions up to there? So that is the important part of the problem, right? Setting up the triple integral, after which it kind of becomes routine. No questions? All right, let's do z first. Okay, please don't spread this out carelessly because the first one depends on r. So the innermost integral r to 6 minus r square 1 dz, and this shouldn't surprise you because the separation between these two surfaces defines the height of the solid. Okay, if you go to this picture, this is the height. Okay, once you have this done carefully, now we can go and do your separation thing. Okay, so now the remaining part would be 0 to 2 pi, because theta and r, they are independent of each other. Okay, and 0 to 2, just don't forget this extra r out there. So 6 minus r square minus r times r dr. So that's 2
Why would you
pi,
move the d theta to the very outside?
because theta and r are not interacting with each other, so you can separate them out. I mean, there's no, the word outside there has no significance. You could put it here if you want. All I'm doing is just, separating those two terms. So whether it's kept first or last, it doesn't matter.
Okay, thank you.
Yep. You cannot do this if r depends on theta or if theta depends on r. Then you have to do it one by one, right? So I think we did this in polar coordinates as well. Whenever we had r and theta kind of sitting independent of each other, just do it one at a time, as in the same step, but you don't have to do it as inner and outer. You could just separate and do it. So, all right. So let's put this back here because I already wrote the 2 pi. And the remaining terms would be the integral from 0 to 2. There is a 6r minus r to the 3 minus r square dr. Okay. That's going to be 6r square over 2, which is 3r square minus r to the 4 over 4 minus r to the 3 over 3 from 0 to 2. Okay. And plug in the limits. Luckily, the lower limit is 0, so only have to worry about the upper one. So it's going to be 2 pi times 2 square is 4, 4 times 3 is 12, minus 2 to the 4 is 16, over 4 is 4, minus 8 over 3. Okay. Once again, I'm not very excited about multiplying 3.14 and dividing it by 3 and so on. Just, write a clean answer. This is 8 is 24 over 3, 16, that's 32 pi over 3. Okay. Is that right? 8 is 24 pi over 24 over 3, 24 minus 8 is 16, 16 times 2 is 32. Yep. Try to minimize use of calculator in these kinds of situations. The answer looks much better in this form than bringing in 3.1415 and dividing it by 3. Okay. Just a suggestion. Okay, so any questions on the setup or the iterative process? All right, here is a problem which we kind of set up last time, but did not want to do it because it was supposedly a little difficult to do in XY, okay, XYZ. So let's try to do it using cylindrical. Can you try to set it up first? So you should be able to look at the problem from last week and see what the picture looked like. And, it was on worksheet 9, which was, where is it? Worksheet 9, right here. Okay. So this is what we did last week. Okay. This was first example which we did as a motivation for today's lecture. So z equal to 9 minus x square minus y square above the plane z equal to 4. Okay. So if you have those answers with you, you could refer back to that and come back to this. So can you try to do it first and then I'll catch up. So all these are copied from our last worksheet. Okay. So who can tell me the limits for R and Z? I give you the limits for theta. That's my part of the deal here. Okay. Who can, start this problem by telling me what the lower and upper limits for Z would be? I mean, you're looking right at it, so there is nothing to really.
Sorry.
Yeah.
How
What's that?
do you know that x squared plus y squared equals square root of 5?
Oh, I just copied it from worksheet 9, but I could do it. So this is, again, the intersection of these two. So it's 9 minus x square minus y square equal to 4. Anytime two surfaces intersect, set those equal. Okay.
Okay.
So if you move these two to the right side, bring this here, you get x square plus y square equal to 5. Yep.
Thank you.
What did I write earlier? Is it what I wrote or something else?
Yeah, you wrote square root of 5 instead
Oh,
of 5.
sorry. My bad. Thank you. So this is r square equal to 5. Okay. So r equal to not plus or minus square root of 5. All right. Okay. So now that, okay, what are the limits for Z here? I know maybe it's too obvious. Is that why you're not answering? Somebody who has not answered yet could, use this. Yeah.
It's 4 and then 9 minus x squared minus y squared.
Okay. Can we replace that minus x square minus y square with something more appropriate for this problem? What will be that?
Minus c. I mean minus r, sorry. r squared.
All right. Some of you still believe that x square plus, not you, but some of you still believe that x square plus y square is r. Okay, you need to kind of keep your notes next to you when you're writing it. That's one of the good things about an online things like, you don't have to memorize things, just look it up, right? So it's r square, not r. Okay, and r goes from 0 to square root of 5 because of this calculation I've done here. Theta goes from 0 to 2 pi. Okay, do we have everything? And yeah, so we are still finding the volume. Okay, that's the triple integral of 1 dv. And here again, z depends on r, so just be careful. Okay, so 4 to 9 minus r square, 1 dz, 0 to square root of 5, and 0 to 2 pi r dr d theta. And more real estate. Yep. Okay, so the innermost integral is the height. Okay, there is absolutely nothing challenging in these integrals, so that's why I'm kind of doing it fast. This is pi minus r square, that's the height. Okay, and now we could go ahead and do our stunts of separating these things. So it's 0 to 2 pi d theta and 0 to square root of 5. Just look out for this extra r here. Okay, so it's pi minus r square r dr. So that's the height times the radius term and then the angle out there. Okay, so that covers the entire solid, and that's equal to 2 pi times, no, not so fast, integral from 0 to 5r minus r to the power of 3 dr. Okay, and that is 5r square over 2 minus r to the 4 over 4, 0 to square root of 5. Okay, the good thing is that with an even exponent, the square root kind of behaves nicely. Okay, so it's 2 pi times square root of 5 square is 5. So that's 5 times 5 is 25 over 2 minus 25 over 4. Square root of 5 to the 4th is 25. Okay. So this is 50 over 4. 50 minus 25, 25, dot, dot, dot. That's going to be 25 pi over 2. Did I get all the numbers there? 50 minus 25 is 25. There's a pi and then there's a 2/4. That's a half. Okay. Again, kind of restrain your temptations to use a calculator. Okay. That's a good answer there. 25 over 2 pi. Okay.
For the bounds for z, would it also work if we change from 0 to 5 minus r squared?
It would, yes. It's the same solid, yes.
Okay.
As long as the height doesn't change from 5 minus r square, if you, any kind of combinations that will maintain the same height would work here.
Okay, thank you.
Yep. Any other questions? You can see these problems are getting easier and easier. That's because, using the right coordinate system. Okay, you try to use cylindrical coordinates for a rectangular box, then you would know the pain of what happens if you don't use the right thing. So it's all horses for courses. Okay. Okay, now let's see what else. This is our favorite ice cream cone problem, which we did last week and we couldn't do because it was getting a little rougher in terms of the integration. Okay, can you try this using cylindrical coordinates and see whether it's easier? Okay, so the picture, again, this is copied from worksheet number 9, so you should be able to see the same picture there. Okay, but if you don't want to go back there, here is the problem. So you have a hemisphere, there is a cone, and this is z equal to the square root of 8 minus x square minus y square. And this is the cone, z equal to square root of x square plus y square. If you want to draw the axis, it's going to be centered here. Okay, so x, y and z axis. And we also figured out that the intersection of these two is a circular disk. Which again is the intersection of those two that think that was given by x square plus y square equal to 4. Okay. But now we are going to really compute it. We are not just setting it up. So which means that choosing the appropriate coordinate systems is a very important part of the decision making. Okay. If you were just set it up, nobody cares in which ones you set it up. Okay. But if you're going to compute it, you need to get something that is doable, right? So I think at this point, cylindrical coordinates is a better choice. Okay. Once you start, or once you decide to use cylindrical coordinates, everything should be in terms of those coordinates. Okay. You cannot have bits and pieces in x and y and then some pieces in r and theta. Okay. There are certain things in math which you cannot violate. Okay. Cylindrical coordinates means everything should go into those 3 letters. Okay. So I think some students in the past, they would keep x and y here, and then they will have r and theta in some terms. Okay, it's a mix of all kinds of coordinates. You cannot have that. That's illegal. Okay. All right. So this is the crucial part of the problem. Okay. As usual, I'll do the difficult one. And you need to tell me the remaining 2 limits. Remember that anything you say should be in terms of the new coordinates. Okay, no more x and y. So what will be the limits for z here?
Would it be r to square root of 8 minus r squared?
8 minus r square. Good. So this is r and square root of 8 minus r square. Okay.
And then would r be 0 to 2?
Very good. Yep. Okay, so our job is almost done, right? I mean, now it's a question of just putting it together, doing some integration, which you have been doing for the last how many ever years. Okay. These are what you call as kindergarten level integrals, right? So anybody can do this integrals. Okay. So the setup for the volume would be the triple integral of 1 dv. Okay. Remember, you have to do z first, which is probably the only term where you might see some level of integration, you know, if you want to call it that, you know, oh, I've got some hard integration here. Okay. That square root of 8 minus r square might be something which, well, could be a little harder. Okay. Not too bad. R dr theta. If you forget this r here, then it's a different story. Okay. Not only that you're going to get a wrong answer, but you're also going to spend a lot of time doing a pretty insane integral. So there are 2 things that could happen if you forget that r. So r goes from 0 to 2, theta goes from 0 to 2 pi. Okay. Remember, I'm not separating anything at this point because my z depends on r. Okay. Let's do that carefully, and then we can do our magic. Okay. So in this case is just the separation between the 2 surfaces. That's a height, r2 square root of 8 minus r square, which is square root of 8 minus r square minus r. Okay. And I hope all of you agree with me that, you know, things like this are not allowed. Okay. I mean, we have come a long way in math at this point. You know, there are things that you should know are kind of gross violations of federal laws here. Okay, so you cannot do that. Okay. Okay, so we can separate the 2 now that we only have r and theta. They don't depend on each other, luckily. Okay, so that, and then 0 to 2 square root of 8 minus r square minus r r dr. Okay. When you get a term like this, try to do it carefully, slowly, take your time. Okay. There's nothing going on there. That's just 2 pi. What I would do is I'll just separate these two into 2 terms. Okay, there are places where you can separate. Addition, subtraction is 1 term. So 8 minus r squared times r dr minus 0 to 2. Then you have r times r, which is r square dr. Okay. So there is, again, nothing fancy here. This is r to the power of 3 over 3 from 0 to 2. Okay. So that term is just 8 over 3. So if out of the 3 terms, we have conquered all but 1, right? The only term that remains is this term, which kind of looks a little rough when you look at it first. How would you do this integral?
Use substitution.
Use substitution, right? I mean, looks like you cannot keep that down. Okay, u equal to 8 minus r square, du is negative 2r dr. Okay, so we just need r dr, so negative 1/2 du equal to r dr. Okay, or if you like doing in terms of, I don't know how you learned in your high school, if you like solving it as dr equal to negative 1/2 du over r and then plugging it in, okay, it's going to give you the same answer. Okay, or okay. All right. Sorry.
Bless you.
Oh, thank you. Since I'm sharing the screen, I cannot mute from screen. All right. So it's equal to 2 pi times. So I'm going to do this in terms of u first. So it's going to be square root of u. That's u to the 1/2. And then you have a negative 1/2 du minus 8/3, which came from the previous step. And that's 2 pi times negative 1/2. Integral of u to the 1/2 is u to the 3/2 over 3/2. That's 2/3. And then u to the 3/2 would be 8 minus r square to the power of 3/2. Okay. Don't forget the exponent of 3/2. Sometimes, students, when they plug things back in, they just write 8 minus r square 3/2. And r goes from 0 to 2 minus 8/3. Okay. Can say I'm in no hurry here, right? I'm just taking my time to do this. And that's 2 pi. Okay. Now it looks like I'm going to negative answer, right? You've got a negative in the first term, negative in the second term, finding the volume of an ice cream cone. Well, the math takes care of it, actually. So when you plug in the upper limit, that's going to be negative 4 to the power of 3/2. Okay. 8 minus 4 is 4. Then you have a minus negative. That's luckily a positive term, right? And then you plug in r equal to 0. That's going to be 8 to the power of 3/2. So all is well. Okay. The bigger term is positive. Okay. And you have divided by 3 minus 8/3. Now, if you want, you can write that as your final answer and stop. You don't have to, take your high power calculators out and write any decimals. But if you want, you can clean it up a little bit, okay, in a nice way. 4 to the power of 3/2 is the square root of 64, which is 8, okay, and 8 to the power of 3/2. Okay, these simplifications are optional, so just in case you want to see what this is, right? So this is the square root of 8 to the power of 3, okay, which is square root of 8 squared times 8. Square root of 8 squared is 8, so it's 8 times square root of 8, which is 16 times square root of 2. Because 8 is 4 times 2, right? So this is 2 pi. So this is an acceptable final answer. If you want, you can stop there. Or if you want to polish this a little bit, so it's going to be -8 plus 16 root 2 over 3 minus 8/3. Okay. So that gives you a -8/3 minus 8/3. That's a negative 16 over 3. So that 16 over 3 is actually a common factor. You can pull that out. So that's 32 pi over 3 times square root of 2 minus 1. Okay. Square root of 2 minus 1 is a positive number, so there is no concern that this volume is negative. But again, these two steps are optional. Okay. I did this mainly because of the fact that we are going to do this using spherical coordinates later, and it might be easier to compare the two answers if you simplify it a little further. Okay, but this is okay as well. All right. But forget about all those numerical stunts I'm pulling there. Okay, that's not the point here. Any questions on the setup, the integration, the U substitution, anything? So last week we did the same problem, but we couldn't do it because integral was not easy. Okay, because of the entire circular domain and region. Okay, now we were able to do it with relatively easier techniques. Okay, it might get even easier when we do spherical coordinates. So that's the beauty of this problem. So as we have more tools to handle the same problem, it gets easier and easier. Okay. So I think those are enough examples with cylindrical coordinates. We might see one more example a little later, but right now that's enough, I think. Okay. Any questions about cylindrical coordinates, which is just an elder brother for polar coordinates? Okay, then let's get back to our notes. So these are the examples we did today. Okay, you should practice this just so that you get used to how cylindrical coordinates are used, and then why you shouldn't write x, y, r, and theta in the same integral at any point. Okay, it's either this or that, right? Okay, back to my notes. Now the slightly harder one, spherical coordinates. Okay. Those of you, or those of us who believe that our planet is not flat, okay? Those of you believe that it's flat. I mean, it's a free country, you can believe it, but it's not flat. Okay? I think the latest space mission was spinning us pictures from space that kind of proved it over and over that it's not a flat planet. Anyway, the motivation to spherical coordinates is because of navigational reasons. Okay? Our planet is an almost a perfect sphere. Okay? There are some flat places near the poles and everything, but for calculation purposes, it's reasonable to assume that Earth is a sphere. Okay, so navigational purposes, this is where this entire concept of spherical coordinates first kind of became necessary, and then people understood that it's a very nice mathematical tool for a lot of other applications in physics and engineering. Okay, because using x, y, and z in spherical coordinate or for spherical regions is kind of a pain, especially when it comes to doing the calculations. So the difference between the previous kinds of the previous coordinates that we saw, polar coordinates, cylindrical coordinates, x, y, z, and spherical coordinates is that we need one radius and two angles, okay, which is what makes us a little weird in the first place to start with. Okay, so the notations are going to be completely different. There is no more r, or there is no more x, y, z. Okay, theta is going to be still there, so that's the good news. Okay, so the good news is theta is the same as your polar and cylindrical coordinates. Okay, but you need to pay attention for the others in this. Okay, that's why I'm going to go a little slow, and if you have any questions, please ask. Okay, You don't have to believe anything that is not clear to you. Okay, just unmute and ask. Okay, so let's. This is what we had. Okay, I'm going to kind of do this slowly. So this is your x, y, r theta, and you wrote x equal to r cosine theta and y equal to r sine theta. Okay, that is from polar coordinates. So what we'll do is we will now define x, y, z axis. And define my same point P here. Okay, let's call it P1 so that I could use P for my new point in space. Okay, so P1, and this is R, this is theta. Okay, and I'm going to project it up here in space, and this is my P. Okay, and let me extend my axis a little bit there. All right. So what we'll do is define the radial distance from the center to this point by the Greek letter rho. Okay, so rho is the radius from the center. Okay, so in this case we are assuming that our center is at the origin. It doesn't have to be, but it's just easier for computation if you don't shift the center around. Okay, that keeps our things or calculations a little neater. Okay, so this is rho. This is not P, though. Even if you're going to call it as P, I'm not going to get offended, but it's rho. Okay, so we need an angle from the positive z-axis going clockwise. So this is the weird thing. Okay, there is this angle that we are starting from this is a positive z-axis going clockwise, phi. Okay, so phi is what we call as the azimuth, the polar angle. Okay, it's called the polar angle because in terms of what we refer to in navigational purposes, okay, it goes north pole to south pole. This is much easier if you just keep thinking about Earth and the navigational things as your frame of reference and your understanding. Okay, so phi goes from the north pole to the south pole. So north pole is where it starts. Okay, for those of you who don't know what north pole is, that's where Santa lives, right? And then you go clockwise and you reach the pole where the penguins live, right? So this is going to be phi equal to pi, okay, south pole. And that's where it stops. So in between there's the equator and everything. Okay, so the equator is right here. The equator would be phi equal to pi over 2. Okay, so phi goes clockwise from phi equal to 0 at the north pole, which is at the positive z-axis, to phi equal to pi, which is 180 degrees, okay, at the negative z-axis. Now here is the one fact about phi that you have to get used to. Okay, it doesn't go back. It doesn't have to go back, but I'll tell you why. Okay, so it starts from here, goes through this one sweep, and it comes here and it stops there. Okay, why is that? So let's draw a nice, beautiful picture of a planet. Okay, so assume that's your Earth. Okay, so this is going to be a north pole. This is going to be a south pole. Remember that we are starting at phi equal to 0 here. Okay, and this is the equator. And all of you know that equator is just an imaginary thing that goes around the center of the Earth. Okay, There is no such real thing called the equator. All right. Now, phi is measured in this direction there, okay, equal to 0, and it ends here. The question is, why doesn't it go back? Because it looks like our theta is going from 0 to 2 pi. Why is it that phi is not going from? Why is it that phi is not going from 0 to 2 pi? The reason is that once you reach one of these values here, for example, that is your Arctic circle, some value of phi. So phi equal to I don't know, 15, or let's just call it phi1 so that I don't clutter this up, okay? So phi1 is some point between the North Pole and the equator, okay? Once you reach this point, you can, without moving the value of phi, go around the surface of the Earth and come back to that same place. This is one sweep through theta from 0 to 2 pi. Okay, so I didn't move from my phi. I was at some point in the Arctic circle. I just went around every possible value of theta and I came back there. Okay, then I moved to another point, say phi equal to phi2. We are still in the northern hemisphere. I do another sweep and I come back there. Then I reach the equator. Maybe this is the Tropic of Cancer there, okay, which is around 23 degrees. Then I reach the equator, okay. I can go around the equator, come back here. That is also a full sweep of 0 to 2 pi. Go to the Tropic of Capricorn there. Okay. Go a full sweep, come back there. And maybe an Antarctic circle, but you get the point. So no matter which value of phi you're picking, okay, you can go around the whole planet and come back to your starting point, which sweeps through the entire 0 to 2 pi. So by the time you start from the North Pole to South Pole, you have covered the whole planet. There is no need to go back from South to North Pole. There'll be just a double counting, okay? So as you sweep through from phi equal to 0 at the North Pole to phi equal to pi at the South Pole, okay? We cover 0 to 2 pi for theta for each value of phi. Okay. So there is no need to go back from the South to North Pole, or no need for phi to be 2 pi. Okay, the maximum value of phi is always phi equal to pi. Okay, it could be less than that. So if you're talking about a hemisphere or a quarter sphere, okay, then it's going to be less than pi, but the maximum extent to which your angle phi can go is from 0 to pi. Okay, that's only new thing in terms of the coordinates. Okay, the rho is radius, okay, which goes from the center to that point. So there is nothing really new in terms of what radius would mean, right? For a cylinder, radius is the distance from the center to the edge, and this is the center distance from the center to the outermost point of the sphere. Okay, theta is still your theta from polar coordinates, cylindrical coordinates. It goes from 0 to 2 pi, no change there. Phi, the polar angle, goes from 0 to pi, because for each value of phi, you're going to go around and come back, and without a second trip back from the South to the North Pole, we are done with the whole planet. Okay. So the summary of our spherical coordinates so far, and then I'll see if you have any questions. Okay. So the radius is always positive. We're not using r anymore, it's rho, okay, but it's the same concept. Theta goes from 0 to 2 pi. This is what we call as the angle of the azimuth, or the azimuthal angle. Okay, so whenever you talk about the position of an aircraft in the sky, we say that there is so many degrees north, so many degrees east. Okay, one of the angles is the angle of the azimuth, and the other one is the polar angle. Okay, and 0 less than or equal to phi less than or equal to pi, not 2 pi. Okay, if you use 2 pi, you'll get all kinds of nonsense as the answer, including 0 volume for a sphere. Okay, you don't want that, right? So 0 less than or equal to phi less than or equal to pi, not 2 pi. And this is what we call as the polar angle. For obvious reasons, it goes from pole to pole, okay, north to south pole. That orientation is important because your theta is counterclockwise. Okay, this is the same as the polar coordinates and cylindrical coordinates. This one is a clockwise orientation angle, okay, from the positive z-axis all the way to the negative z-axis. Okay. Any questions on those three notations for spherical coordinates? So there is no r, there is no x, y, z. Okay, we have rho, theta, and phi, or some people call it phi. I don't know which one. Phi. Any questions up to there? We're not done with things here. Okay, so any conceptual questions? The next question is, what is dv? Okay, because in cylindrical coordinates it was just r, dr, d theta, dz. How do we do a dv calculation for spherical coordinates? Okay, that's one of the slightly crazier things about spherical coordinates. Okay, and before we do that, let me kind of copy this picture down here because we need that. Okay, so first we need to convert everything. So this is your x, y, z, and this was your p1, r, theta, and then this is your p, rho, and this is phi. Okay, my pictures are getting worse and worse, but okay. So what I'll do is I'll draw a line parallel to this line OP1. Okay, so this red line here, that's same as this. So this is R, okay, and this height is Z. Now that we have a new coordinate system, we have to write everything in terms of those letters. We cannot use any of the old letters anymore, right? Okay, now let's look at this triangle here. Okay, this triangle, the one that I've just shaded using red. And if you take the cosine theta and the sine theta out of those, oops, cosine phi and sine phi, sorry. Okay. All right, so let's see what cosine of phi will be. Cosine is adjacent side over hypotenuse. Okay, adjacent side to phi is going to be z, so it's z over rho. Okay, sine of phi is opposite side over hypotenuse, that's r over rho. Okay, this is a systematic way of deriving spherical coordinates. This way you don't have to memorize a ton of things. Okay, we don't memorize anyway, but I'm just saying, if you use this picture, it's a very smooth transition from what you know to what you don't know. Okay, so use a right angle triangle, use your high school knowledge about trigonometric functions. Okay, so cosine is adjacent side over hypotenuse, sine is opposite side over hypotenuse. This gives you z equal to rho cosine phi. Okay, so that's a conversion of z in terms of rho and phi. Okay, so that's one thing done. The other one gives you something even more neater. It tells you the radius in polar coordinates in terms of spherical coordinates. Okay, so this r here, or this r down here, Okay, that's rho cosine phi. So, oops, what did I just do? Rho sine phi. I wrote sine here and I rho sine phi. Okay. Why is that important? Because you know that from cylindrical coordinates, x equal to r cosine theta. Okay, so r is now rho sine phi cosine theta. Y equal to r sine theta, which is rho sine phi sine theta, and z, which you just got here, is rho cosine phi. Okay. This is a conversion from xyz to r theta phi. The conversion chart. Okay. So you can still use your cylindrical coordinates, okay, for xyz, but as soon as you do that, you have to remember that you need to change your r in terms of rho and phi. Okay, because r is not used anymore. R is this. Okay. And if you do a simple calculation, x square plus y square plus z square, you get rho square sine square phi cosine square theta plus rho square sine square phi sine square theta plus rho square cosine square phi. And if you combine these two terms, that's going to give you rho square sine square phi times cosine square theta plus sine square theta. Okay. Now this, hopefully all of you know, this is equal to 1. So we have rho square sine square phi plus rho square cosine square phi. Okay. And you can pull out a rho square from this, and that's equal to sine square phi plus cosine square phi, which is also equal to 1. And that's rho square. Okay, so we have a similar kind of term from cylindrical coordinates where x square plus y square was r square. You have everything here. Okay, x square plus y square plus z square equal to rho square. Okay, which is also a hint that if you see this term at any point, it's a hint for spherical coordinates. Okay, if you just see x square plus y square, I think cylindrical coordinates might be more appropriate there because, you know, spherical coordinates has this extra z thing which makes it a little painful if you don't have a perfect setup. Okay. So I did my xyz conversion in terms of rho, and rho is the square root of x square plus y square plus z square. Any questions up to there? Okay, now the bigger question is what is dV? Okay, that's the only thing remaining, and then we can start computing volumes and masses. Okay, what is dV? Remember, this was simple, just dx dy dz in rectangular coordinates. Okay, this was r dr d theta dz in cylindrical coordinates. Okay, so it got a little harder, but not too bad. Okay, what is this in spherical coordinates? Okay, it's probably the only crazy part of spherical coordinates, that the dV is a little bit non-intuitive. Okay, so let me try to derive this quickly without making it too technical. Okay. So as usual, what we'll do is we'll take a small chunk of a spherical volume. Okay, so remember this angle is phi. Okay, so this small angle is d phi. Okay, this is rho. So if you take a small 3D chunk along this radial line, this increment is d rho. Of course, you have to make it 3-dimensional, so that's do it carefully. Okay, and of course there is so D row is the, let me use different colors now. D row is this red thing. Okay, we have two more things here. There is this side, and also there is the blue side. Okay, so we have to deal with each of them. Did I just repeat one of those? No, the green side should be, wait a second. I think I drew this one parallel to the red one. The green side should be this one. Now we have all three. So the green one, which is this arc here, okay. Just like we did for the polar coordinates, it's going to be the radius, which is rho times angle. Okay, so this arc length is the radius times the angle in radians. Okay, so it's going to be rho d phi. The blue side is going to be the projection of your typical dr in the xy plane. Okay, so this is your d theta. This side is what is projected up here. Okay, and this length, this is r, and that's d theta. This is going to be r d theta. But r is rho sine phi. Okay, remember that r is not allowed in spherical coordinates. R was rho sine phi up here. Okay, this one. So this blue side is going to be rho sine phi d theta. Okay, so the overall volume of that three-dimensional chunk you see up there is going to be the product of all these three: the red one, the blue one, and the green one. Okay, so dv is equal to d rho. Okay, that's the easy one. That's just an extension of the radius times rho d phi times rho sine phi d theta. Okay, so if you multiply these together, you get rho square sine phi d rho d phi d theta. Okay, and that's crazy, right? Because we had a very simple expression, which was which is just up here. Okay, rectangular coordinates, just very intuitive: x, y, z, dx, dy, dz. Right? Cylindrical coordinates got a little bit complicated because of how the curved area looks in polar coordinates. Okay, instead of just dr d theta, it was r dr d theta. All right, that's not too bad. Okay, but now with spherical coordinates with two angles and one radius, okay, we need enough terms to make up a volume unit, because remember that d theta, d phi, all these are unitless. Okay, the volume has to come from the radius alone. So it's a rho square times d rho, which is going to be the only contribution towards the units there, or the dimensions there. Okay, so that is your dv. So it's not rho sine phi, it's rho square sine phi d rho d phi d theta, or d theta d phi. Okay, any of those combinations is possible, and that kind of finishes everything for spherical coordinates. Any questions on any of those? I don't expect you to know any derivations, but I don't want to just tell you, oh, just believe that dv is equal to this without any justification. So that's why I just went through this. Okay. Just summarize spherical coordinates before we start doing examples. Remember that your spherical coordinates are made up of a radius and two angles. Okay. So x equal to r cosine theta would be now rho sine phi. Yeah, please go ahead. I didn't hear. Was there a question? Oh. Rho sine phi cosine theta. Okay. Y equal to rho sine phi sine theta z equal to rho cosine phi x square plus y square plus z square. I think somebody is asking a question, but I cannot hear it. Okay, they're breaking up. All right, and dv is rho square sine phi d rho d phi d theta. Radius is strictly positive. Theta goes from 0 to 2 pi, no change. Phi goes from 0 to pi. And that is spherical coordinates. Okay. Somebody has a microphone on. It's because they have any questions or just by mistake? I don't know. All right. Okay. Any questions about any of these concepts before we start doing some problems? Okay. Do you know what the volume of sphere of radius r is from your high school, middle school?
Is it 4/3 pi r cubed?
Yes, 4/3 pi r cube. Okay. But I don't think anybody told you why it is 4/3, right? I mean, that seems a bit mysterious. Why is it 4/3? Why is it not just 4 pi r cube or just pi r cube? So let's see what exactly causes this 4/3 and everything. And before I do that, let me just give you a quick note about how spherical coordinates are slightly different in navigation. Okay, just because it's easier for them that way. The equator is treated as the reference point for theta. Okay, sorry, reference point for phi. So phi equal to pi/2 for the northern hemisphere, and negative pi/2 for the southern hemisphere. Okay. For us, for calculational purposes, it's easy to just go from 0 to pi, but for navigational purposes, it's easier for them to just go above and below the equator. Okay, so 90 degrees north or 90 degrees south of the equator. Okay, they don't use radians, so let's be more sensible there. Okay, 90 degrees north and 90 degrees south of the equator. Okay? That's the positive and negative 90 degrees. And again, for azimuth, they use the prime meridian as the reference point. Okay, so this is theta equal to 0, and they go left and right of the prime meridian. The prime meridian passes through Greenwich, England. If you have done some basic geography, okay. So it goes from negative 180 degrees to positive 180 degrees. Okay, so this is to the left of the prime meridian, and this to the right of the prime meridian. Okay, so the overall it's 360 degrees going around the Earth, but it's kind of split into two based on the reference point of Greenwich, England. Okay, so that's because it's easier for them to navigate that way. We don't want to use negative pi to pi. It's easy for us to use 0 to 2 pi. Okay, so convenient for us to do this. Okay, but no matter what, you are going around in circles. If you start from one point, okay, and if you go around, you will eventually get back to the same point. Okay? All right, just want to let you know that in case you see a map and then you're wondering why some angles are negative, that's because of the reference point being equator and the prime meridian. Okay, okay, now let's see how this is going to hold up. Okay, so let's find the wall. Any questions before I do that? So before we do those problems in the worksheet, find the volume of a sphere of radius capital R. Okay, I should be very precise about what kind of sphere it is. It's centered at the origin. Okay, the formula for the volume of a sphere is not going to change, but it's convenient if you don't shift the origin and keep it somewhere else. So centered at the origin. Okay, so that's the only thing we know, right? The radius. Everything else should come from the spherical coordinates, and the volume is just the triple integral of 1 dv. Okay, you could try this using cylindrical coordinates. It's not going to be too easy because the problem with cylindrical coordinates is that it's based on two flat surfaces at both ends. Okay, this is a cylinder, this is a sphere. Okay, so if you are trying to use cylindrical coordinates here, it's going to create problems at the two ends. Okay, because so not appropriate. Okay, you could do it, but it's not appropriate. Okay. So we'll use spherical coordinates. So your radius, remember you're using rho for radius. Okay, it's going from 0 to r. Theta is your full angle, the azimuthal angle that goes from 0 to 2 pi. Okay, and phi goes from 0 to pi. Okay, here is the other crazy thing. If you're a physicist and if you take physics classes, the phi and theta they are interchanged. Okay. They use theta for phi, phi for theta. So it's crazy. Okay, and dv is rho square sine phi d rho d phi d theta. Okay, the good thing is all these are constant limits. There is no rho dependence on theta or phi, phi depending on theta or rho. Okay, theta, all of them are separate. So as soon as we write the integral, we can separate it out. Okay, so the volume would be the integral from 0 to r rho square d rho, 0 to 2 pi d theta, and 0 to pi sine phi d phi. Okay, because it's the triple integral of 1 dv, and all the three components kind of separate themselves because they're not related to each other. Okay, and each of these are just calculus 1 integrals. So this is going to be rho to the power of 3 over 3 from 0 to r. That is one piece of our answer, right? We had a 4/3 pi r cube, so that's nice. This is 2 pi. Integral of sine is negative cosine from 0 to pi. Okay, so that kind of makes us nervous. Are we going to get a negative volume? You know, how does the math take care of itself? Okay, so this is r to the power of 3 times 2 pi. Let's put that negative out here just to be safe. Okay, don't just erase a negative because you think the volume is going to be positive. You're like, oh, just somehow cheat and right. So the negative is still there. Now plug in the limits. It's going to be cosine of pi minus cosine of 0. Cosine of pi is -1. Cosine of 0 is 1. Okay, so it's 3. Cosine of 0 is 1, and then in the second quadrant, cosine is negative. Okay, so cosine of pi is -1. So this overall thing is -2 times this negative out here becomes positive, and then you have another 2 here, and that's 4/3 pi r cube. Oh, that's easy. Okay, use the right coordinates. The answer is so easy, right? Any questions on that? Now, if you try to put phi going from 0 to 2 pi, you're going to have a problem, because then the cosine of 2 pi is 1, cosine of 0 is 1, they'll become 0. You get a volume of 0 for a sphere. Okay, so there are actually some red flags if you get wrong limits. Okay, so if you use 0 less than or equal to phi less than or equal to 2 pi, the volume would be equal to 0. Okay, that's not true, right? The volume of a sphere, it's a positive number. Okay, it has to hold something inside it, so it needs to have volume, and that depends on the radius. That's given by this. Okay. Any questions on that? So all that hard work pays off, right? I mean, look at the integration. It's so easy if you know what dv is. Let's do one more example outside of the worksheet. Okay, example 2. Find the volume of part of the sphere. Again, feel free to unmute and ask questions if anything is not clear. Okay, spherical coordinates, I know it's a little bit kind of not the most natural way of thinking. Okay, part of a sphere of radius r, centered at the origin. In the first octant. Okay, so you can think about it as taking an apple and first you cut it half, okay, across the equator, and then the upper half here again slicing it into 4 chunks, and you're taking just one chunk, so it's 1/8. Okay, so talking about 1/8 of a sphere. But which 1/8 this is? This is the most convenient 1/8. It's the one in the first octant, so everything is positive. Okay, so the first octant is what we refer to as x greater than or equal to 0, y greater than or equal to 0, z greater than or equal to 0. Okay, in terms of what we are doing, this is the first quadrant. Okay, and this means you are in the upper half plane. Okay, it's above the xy plane. And for a sphere, I can think about it as above the equator. Because the z-axis defines the phi angle. Okay, so that should help you. The first quadrant is this, okay, on the xy plane, and this is above the equator, which helps our angle phi. Okay. The radius is easy, so it's 0 to r. Okay. Usually that is the easiest of the 3 variables. And you know the answer should be, if you were to cheat, okay, the expected answer would be 1/8 of 4/3 pi r cube, right? The math has to agree. It's 1/8 of a sphere, so it has to be this, and that's 4/24, which is pi r to the power of 3/6. Let's see if we get that answer. Okay. So can you tell me what the limits for phi and theta would be?
Would they
Mhm.
both be from 0 to pi over 2?
Very good. Both of them are from 0 to pi over 2. Okay. Theta is from 0 to pi over 2 because it's the first quadrant. So on the xy plane, it's just going from 0 to pi over 2. Phi is going from 0 to pi over 2 because it's above the equator. Okay, so you're starting from the North Pole. You don't go all the way to South Pole. You're stopping at the equator. Okay. So let's see what happens. Then the volume would be the triple integral of 1 dr, but you can just separate them out as soon as you see it.
Sorry, I have a
Yeah.
question.
Mhm.
I thought that for the theta it would go from 0 to pi, but I'm wrong. Could you explain how it works, like why it goes from 0 to pi over 2?
Oh, theta is the angle on the xy plane. So this is your. So theta usually goes like this. Okay, 0 to 2 pi. That is one full rotation.
Yeah.
Agree?
Yeah.
In the
I
first
agree.
quadrant, you're only going up to here because this is what restricts the first octant. So the first quadrant would be just the part where both x and y are positive.
Okay,
And
makes sense.
yep, the y-axis is 90 degrees, so pi over 2.
Okay,
So
yeah, thank you. Yeah.
Yep. So 0 to r rho square d rho. Okay. 0 to pi over 2 d theta, and 0 to pi over 2 sine phi d phi. Okay. This is again rho to the power of 3 over 3, so it's r cube over 3 times pi over 2. Okay, this one. Integral of sine is negative cosine. Okay, don't try to hide the negative thinking, oh, the answer is somehow wrong or something. Just write everything as you know it, right? Integral of sine is negative cosine, and if you do the math right, it should take care of itself. This is pi r to the power of 3/6. There is a negative there, times cosine pi over 2 minus cosine 0. Okay. Cosine pi over 2 is 0. Cosine 0 is 1. Negative times negative is positive. So that's pi r to the power of 3/6. Okay, which is what we expected, right? My claim was that it was going to give me 1/6 of the volume of a sphere, and that's what you get.